Alright, hey everybody, so this is going to be proposition 2 of book 1 from Euclid's Elements, which says it's, again, another construction proof. So to place it at a given point as an extremity, a straight line equal to a given straight line. So in other words, if you're given a straight line and just some point that is not on the line, we want to recreate off of this point A another line that is the exact same length as BC. One kind of cool thing that I was just playing around with this is that you can even put this point A, like if you were to extend BC and then place A on that extension, this proof or this construction still works, which I think is kind of cool. Okay, so let's see here, right, and this bit in here in the square brackets as an extremity. So in general, from the translation that I have, it's the Heath translation. Usually these square brackets, if it's kind of like placed somewhere like in the introduction or like what we're setting out to do, it means it's something that Heath himself had added into the translation, so it wasn't there in like the original Elements, but he added it sort of for clarity. So just I take that line as an extremity to just mean that the point A is not actually on BC. I haven't played around with that, whether or not this construction still works with A being on BC. Alright, so let me just jump into it. There's a little bit of figuring out that I have to do because this ends up being something of a large diagram, and I want to be able to fit everything onto the page. So it might get a little clunky here or there. Alright, so we have our point A, we have our line BC. So how do we start this off? Well, to begin, from point A to point B, we join. We join A and B. Alright, so step 1. Join AB, or construct, I guess, maybe, AB. And yeah, again, that comes straight from a postulate. How do we know that we can do that? Well, that's just postulate 1. Between any 2 points, you can construct a line. So at some point with something like this, with these sort of what I think are maybe obvious steps that can obviously be justified, I'll stop saying like, oh, this is from postulate 1 or definition 15 or whatever. But for now, we'll keep adding those in, because that's kind of like the beauty of the Elements, is that sort of rigor of realizing like, hey, I need to be able to justify just about every single step. Alright, what's next? So next is we create the equilateral triangle DAB. So an equilateral triangle of side length AB, which we're able to do because of proposition 1. So create or construct equilateral triangle DAB. And this comes from proposition 1, book 1. Alright, so rather than doing the full construction, which is short, it's just making 2 circles, one with center B and radius AB, the other with center A and radius AB. I'll just do kind of like the relevant points that are going to give us the line that we want. I'll do enough to make it obvious what we're doing. Because part of what I like about all of these proofs is how pretty they are. So yeah, like it, and I think that they're even prettier if you put in the full circles, but the diagrams can end up being quite large and complicated if you're putting in every single little thing. So I'll just put in enough, because my goal is to just try to honor sort of like the beauty of the Elements. Let's see, is my page gonna stick? Stay. Okay. Right, what's next? So we've only done 2 things so far. Step 3, what are we going to do? So it says let the straight lines AEBF be produced in a straight line with DADB. So in other words, what it's saying is, oh, and I didn't actually create my triangle, but I can create the triangle and then do this next step, because this next step is saying take these sides, DA and DB, and just extend them out. So I'll extend them to here. Hopefully that's long enough. We'll see on the next step. So here's equilateral DAB with the extended lines. Let's see. And what did we call the lines? We called them AE and BF. So A here's line goes out to E, and then B goes out to F. So I'll just say step 3, extend dA and dF. And this is a postulate. This is postulate 2 that says that we can do that. It says that any line, you can just extend it indefinitely. That's all postulate 2 says. Again, they just didn't take anything for granted. It's the modern, it's the foundations of the modern mathematical rigor. All right, next, looks like we're going to make some circles with center B and distance BC. So, in other words, we're going to construct the circle with center B and radius BC. That's what's meant by distance BC. So, BC is the original line that we're trying to recreate over at A. Just to kind of remember, I'm going to make this AE a little bit longer because just eyeballing it, it's starting to look a little bit like the same length as there. It just looked strangely the same length as BC, and that's actually where we're going to create the line. Okay, so constructing circle with center B and radius BC. This one I think I can make the full circle and it will, yeah, not clutter things up too much. Yeah, all right. And we call this circle, they called this circle CGH, and really G is going to be the intersection of this circle with DF. So right here is G. And then again, they just designated circles by 3 different points. So C, G, and then H is, I don't know, wherever you want it to be. It's not that important for the proof. It's just their naming convention for a circle. So constructed B, BC, and then there's another circle coming, right, with center D and radius DG. So here's D, center D, and then DG is sort of this line that we just cut off. So we need to make a fairly large circle. And this one's going to be too big for the full page. Oops, I'll do as much of it as I kind of can, just to try to make it as pretty and as close to the original as possible. It's that great big circle. Alright, so step 5, we construct DG. And I guess the second part of step 4 is labeling this point, so which I didn't do. So let G be the intersection of DF with this new circle, BC. Sorry. And then same thing here. Yeah, look how close it was. Oh man. Because this point right here, let me shift some things around so it's not. This is line E, DE. But this point right here, we're going to call this L. So they said, the Greeks said, we'll call this big circle GKL. So G, L, and then K is wherever you want to place it. But the important part is we're making L be the intersection of AE with this circle DG. And then 6, claim AL is the required line. In other words, AL equals BC. And hopefully you're saying, yeah, well, how do we know it? Yep, once again, that's exactly what Euclid was anticipating you to say. All right. So let me see if I have a way of getting all of this on the screen. I'd like to keep as much on the screen as possible. Keep the diagram on the screen, keep the instructions on the screen, and then put the proof on the screen. Okie dokie, and how does the proof run? Well, first of all, we know that BC is equal to BG because It's the radii of the same circle. So Euclid would have, if he justified it, at least it looks like in my translation that this isn't justified, but that's the definition 15, definition of a circle. So BC equals BG. What else do we have? Well, DL equals DG also, for the exact same reason. They're just radii of the same huge circle. So DL equals DG. Why? Same reason. All right. Next, we also know that dA is equal to dB. Why? Because they're both sides of an equilateral triangle. We constructed that equilateral triangle. We made that as an equilateral triangle. So we know that dA equals dB. This is by construction. When we created an equilateral triangle, they're created to be the same. All right. And from here, Euclid just kind of concludes. He says, well, basically, like, this is enough to say that these are the same, and he kind of gives the justification, and it's, you know, it's poetic the way that he gives the justification. It's not super mathematically clear. But the idea is basically this. Well, if we take a look at the line DG, which is a straight line, we know that DG is equal to the line segment DB plus the line segment BG. Similarly, we can say something similar of DL, that DL is equal to DA plus AL. Well, from our second step in the proof right here, we said that DL and DG are equal to each other. So in other words, DB plus BG, which is DG, is equal to dA plus AL, which is DL. All right, but we also know that, let's see, what do we know? We know that dA and dB are equal to each other. So you can think of it as like subtracting those off, right? dB and dA are equal to each other, so we can subtract those off, which leaves that BG equals AL. And this comes from common notion 3, which says that if, how does he state it? If equals be subtracted from equals, the remainders are equal, which is saying exactly this. So BG equals AL. All right, great. So what have we shown right now? We've shown that AL is equal to BG, but that's not what we set out to do. We set out to show that AL is equal to BC. And probably it's really obvious to you now how that falls out, because the very first step of our proof was noting that BC equals BG. So BC equals AL, which is what we set out to do. And again, I guess this is, just to justify it, this is common notion 1. Equals equal to equals are equal. All right, and that's that. That's what we wanted to prove. BC equals AL, so we did exactly what we wanted to prove.